Well, good day, everyone. This is Alan Clegg, and we are here for the fourth installation of the webinar series regarding DNSSEC. So thank you all for attending. We're very pleased to have you with us today. And today we're going to be talking about the actual resolution process and how DNSSEC validation actually occurs. So with that said, let's go ahead and get started. So we're going to continue a little bit from what we talked about last week, and we're going to talk about what DNS actually does, what the information that's provided back in the response to a query that we make. So in the response, there are going to be one of four types of answers. There's going to be a positive answer, which means that yes, we got information back in answer to the question, and it was actually the answer to the question that was asked. We're going to get a negative answer, one of which are two possible negative answers, either a no data answer or an NX domain response. So a no data answer is, for example, when you ask for a label that does exist, but you ask for a type within that label that does not. So let's say that you have a web server that has an IPv4 address, but you haven't deployed IPv6 yet. If somebody does a query for example, www.example.com, and they're looking for the resource record with a type of A for an IPv4 address, they're going to get that IP address. But if they do the same query, but asking for the quad A answer, there's not going to be any information, but the label exists. So in that case, the negative answer is going to be a response that has 0 answers in it. It's going to be a negative answer, but it is not an error of any type. The other type of negative answer is an NX domain response. And this is something that you are going to get back if you ask for some data at which the label actually doesn't exist. So if, for example, you fat finger and you accidentally type 4 W's, so www.example.com, the query is going to go off. It's going to hit the authoritative server. The authoritative server is going to see that that does not exist at all. There's no label at the www address, and so therefore you're going to get back an NX domain. You can also get back as a response, you can get back a referral. Now that's along the lines of, thank you very much for asking me that question. I understand what you're asking, but I'm not the actual authoritative server, so I'm going to send you down the line as to where to get the answer. And then of course you can get an error response, and this is going to be not a negative answer, but actually an error, maybe a misformed query, maybe an error along the lines of a refused answer, maybe authoritatively someone has set something that says that they're not allowed to answer your query. Maybe it's something in the fact that the name server itself is broken, and maybe you're going to get back a serve fail. So with each of these types of answers, each of these types of responses, DNSSEC is going to need to be able to prove that what it gives back is actually the correct answer, whether it is an error or a negative, a referral, or a positive answer. So DNSSEC is going to have to be able to prove these for both the positive and the negative answers, and there has to be a way to prove that that data is either good or bad. So somehow we're going to be able to take the data that was returned to us, and we're going to look at it and maybe look at some cryptographic information that maybe was provided with it, and then do some calculation and see that the data is either good or bad. Now, hopefully, and this is the whole purpose for DNSSEC, any bad guy along the path or anyone that's modifying the data for whatever reason is not going to be able to do the cryptographic work that is required to make your DNSSEC signatures correct, and therefore the server receiving the answer is going to be able to do the cryptographic work and recognize that that information was modified or that there's something wrong with it. So we're actually, the ultimate goal of this is to prove that the positive or negative answer that we get back is unmodified since it was sent from the authoritative server. So we're going to talk a little bit today about the DNSSEC record types, but next week we're actually going to go into each of these in great and gory detail. We're seeing that introduced into the DNS specification were the following record types. There is the DNS key, which is the public portion of the key. So if you remember, we talked a little bit about the public and private key pair. Well, obviously we need to be able to make the public portion visible, and so we're going to publish it within the DNS. So we're going to create a resource record that's going to be associated with a zone that is going to contain the public key, and that's going to be the DNS key resource record. The RRSIG is going to be the signature created using the private portion of the key on authoritative data. And we're going to see next week how the RRSIG actually covers a number of parts of the response. It doesn't cover just a single resource record. It covers a resource record set. So if you're not familiar with a resource record set, we're going to talk about that a little bit next week, and it gives you something to look up between now and then. The NSEC record is an authenticated denial of existence. We're going to go into this in detail because the NSEC record allows a negative response of either an NX domain or a no data to be provable. And the problem is, it's really hard to prove a negative. How do you prove that something doesn't exist? So we're going to go into the NSEC record and how that actually works. Well, NSEC, as I mentioned, I think on week 1, was actually a problem for some people because it actually allows the enumeration of all of the data in your zone. And the problem with that is that a lot of people, for contractual reasons or whatever, don't want the entire world to be able to see all of the data in their zone. So the NSEC record actually caused some problems. Well, the fix for that was a new standard of NSEC 3. And the NSEC 3 and the NSEC 3 param records are used to create a hashed authenticated denial of existence. So instead of the enumeration that's allowed with NSEC, NSEC 3 allows you to have the same provable denial of existence, either NX domain or no data, without giving the person on the other end the ability to walk through your entire zone. And then we had the DS record. The DS record is a delegation signer record, and this is actually something that you, as an organization that is deploying DNSSEC, is going to provide to your parent zone. So if you are example.com, you're going to create a DS record for example.com, but you're not going to put it in your zone. You're going to give it to the .com zone, and it's going to be inserted there, and it creates a chain to allow the validation of signatures. And then something that's new, and you may not have seen, even if you've been to my previous classes, the CDS and the CDNS key resource records. These are new. There's a new specification for this, and it's really kind of neat because once you have a chain of validation in place, you're able to see, or you're able to put data into your zone that is provably good. So once you're able to do that, you need to be able to modify the data upstream. So for example, the DS record in your parent, instead of having to contact them out of band, send it in an email or go some web form, why not put that information in your own zone and then allow it to be picked up from your zone and inserted into the parent? So the CDS record and the associated CDNS key records are used to do this. And we will, again, we'll see this a little bit later in the series. There were also a couple of rule changes. So if you're familiar with DNS, you know that we're all about some rules. The biggest rule that was modified is that the DNSSEC records are exempt from the CNAME and other data rule. So if you're familiar with the CNAME record, you know that you cannot create a CNAME at a label where there is additional data. If there's a www.example.com A record, you cannot create a www.example.com CNAME record. You cannot have a CNAME and other data at the same label. This is actually has caused some issues because a lot of people want to be able to say, you know, example.com has the same A record as www.example.com. And a lot of people will say, hey, we'll just create a CNAME that makes the example.com a CNAME to www. You can't do that because example.com obviously has the NS records, it has the SOA record, and it has all of the other associated things at the example.com label. So you cannot have a CNAME and any other data. Well, DNSSEC requires you to be able to do things like sign the CNAME record. So what you're going to see is that you're now going to have CNAME records that are going to be coexisting with RRSIGs and the NSEC records and NSEC 3 records. We'll see this a little bit later. Again, we'll see this next week when we talk about these in detail. But when you look at a zone and you see a CNAME, it used to be you would never ever see another any other resource record type at that same label. Now you will. You will see signatures, NSEC and NSEC 3 records at the same label. Now, you're not going to have to worry about this. Oh my gosh, you know, we're going to have to change our procedures. No, you're not, because what's going to happen here is that the signing process is going to deal with this completely for us. All of the signatures and the NSEC and NSEC 3 records are going to be inserted without us needing to do any additional work. Okay, so now that we see the pieces that are in place and we see a couple of the other resource records that are going to be used to do this, let's talk about how resolution actually occurs. Now, if you've been doing DNS for a length of time, you're familiar with how recursive answers or how recursive servers work. You have a client that does a query to a recursive server. If the recursive server doesn't have any information, it then has to go up to the root and then chase the answer down to the authoritative server that is at the label or that serves the label that you asked for. So in this case, you probably recognize this little diagram. In this case, we're going to be doing things a little bit different. And in this case, we're actually going to be doing DNSSEC validation. Here we see that the client, who may or may not know anything about DNSSEC, is asking the local caching server for the address record of www.example.com. Well, the local caching server, the first thing he does, as always, is look in his cache. Does he have this information available already? And if so, he provides the answer back. If not, he's going to have to go out and do some work. And we're going to skip over the part where he figures out where example.com servers are and go right to the part where we're actually doing the lookup for the A record from the authoritative server for example.com. And now there's something a little bit different here. You'll notice that www.example.com, we're asking for the A record. We don't know the answer. And in this case, we are setting a new bit in the eDNS header. In the eDNS header, along with some other things, is a bit called the DO bit. The DO bit is DNSSEC OK. What this means is that the example.com server, if it is aware, if it knows how to do DNSSEC, and it has signatures for the resource records being asked for, it's going to return those to the server asking the query with the DO bit set. So in this case, the example.com server responds and says, yes, I have the www.example.com A record. And since you set the DO bit, I'm also going to return to you the www.example.com resource record signature that covers the A resource record RR set. So if there are multiple A records associated, they're all going to come back. There's only going to be one signature associated with all of the A records at that specific label. So now in the upper left-hand corner, you'll see this is the, I'm keeping this as track of what is being stored, what is being remembered on the local caching DNS server. So what we see here is that the A record, the IPv4 address record, is remembered, as is the signature, the RRSIG, on that A record. And the function of that, again, is to sign the data of, or sign the resource record set associated with the A records. So the authoritative server that's serving signed zones is going to provide RRSIGs in addition to the data if the client sets the DO bit in the EDNS0 header. And again, this is DNSSEC OK, which says, hey, I understand enough about the DNSSEC protocol for you to go ahead and send me the signatures associated with the data that I asked for, and I will deal with it. Now, the signature, as we have talked about, provides cryptographic provable trust in the data that was signed. Now, as we talked about week before last week, it uses asymmetric cryptography where the public portion of the key is stored in the DNS as a DNS key record. So there is an RRSIG that comes back that was created with the private portion, but needs to be checked with the public portion, which is stored in DNS as the DNS key record. So how do we go about, as our local caching DNS server, how do we go about seeing if that signature, the RRSIG that we received back, was valid? Well, we don't really know anything about this zone, but they gave us back a signature, so let's ask them about the DNS key associated with example.com, because the example.com key is going to be the one that was used to sign the records within example.com. So we ask this with the DO bit set, and example.com provides us back the DNS key record and again a signature on that DNS key resource record. So in our little storage area, we now have the A record and the signature on the A record. We now have the DNS key, which is the public portion of the key that was used to create the signature that we just got. And we have the DNS key signature, which also may have been created with that key. So that's all well and good. And we could go ahead and use that key to prove that the data is that the signature is good. The problem with that, though, is that we don't have any way of proving that the bad guy, if there's a bad guy in the situation, that there's a bad guy sitting on the wire that modified not only the A record and its signature, but is also going to be able to provide us with the key, the public portion of the key that he used, that the bad guy used to create the signature on the data that he wanted us to trust. So the recipient is being asked to validate the data using a key that's being retrieved from the same server and across the same data path that the data itself comes from. So if the bad guy can fake the data, he can probably fake the key as well, because if they go into that trouble, then the sky's the limit on what's going to be done to you. So to be able to prove that the key in a zone was created and inserted by the actual owner of the zone, the new resource record, DS, the delegation signer record, was created, and it was necessary to be able to prove a linkage between the parent and the child. So the DS record resides in the parent zone. So you create the DS record for example.com, but you hand it to your parent. They put it into their zone. That contains a hash of the key that is in your own zone, that's in the child. So instead of having the entire DNS key resource record, it contains a hash. So it's smaller, it's more compact, and it's something that you can store in the parent very easily. So now, to compromise the key in a given zone, the bad guy not only has to compromise the zone, but they also have to compromise the parent. And well, that parent is also going to be using DNSSEC. So that means it's going to have a DS record in its parent, and there's going to be a DS record for that in its parent. So you're going to have to, the bad guy, not necessarily you, but the bad guy is going to have to go and chase all the way up the chain, compromising DNSSEC all the way to the top. And that is something that is very highly unlikely. So we know that we have the DNS key for example.com, but we want to prove that it actually is the DS record, that it is valid. So what we're going to do is we're going to ask the parent, obviously in this case com, we're going to ask for the DS record for example.com. We're going to ask this with the DO bit set. So again, we're going to ask and say, hey, give us the data, but also give us the associated signature. So in response, the com servers are going to give us example.com's DS record, which again is the hash of the key that's in example.com, which we've already retrieved. And we're going to get the example.com RRSIG covering the DS record. Well, that's great, but how do we prove that the example.com, that RRSIG is good? Well, which key was used to create that signature? Well, it's the one for com, not the one for example.com, but the one in the parent. So what we're going to have to do now is we're going to have to ask for the keys, the public portion of the keys associated with that signature. So we're going to ask com, hey, can you please give us your DNS key? And again, we have the DO bit set. So we're going to get back the DNS key for com, and we're going to get the signature on that DNS key. So as you see in our little data storage area, we now have the A record that we were looking for, the signature on that A record, the key, the public portion of the key associated with the signature on the key, the DS record associated with the key, the signature on the DS record that is associated with the key in example.com, and now we have the com key, public portion again, and its signature. Well, that's fantastic. What do we do now? Well, yep, sure enough, we have to do the same query one level up. Hello, root, can you please give me the DS record for the com zone? And again, I want the signatures associated with it, please. Root is going to give us back the com DS record and the signature associated. And again, we're going to store that data. Now, if you're worried about time, because you'll notice that we've done a whole bunch of additional queries, and this is after we've already done a recursive lookup for www.example.com, we are now having to do all these additional queries, and the client sitting out there at the end still hasn't heard anything back from us. There's no, hold on a second, I'm looking for it. He's still waiting while we do these queries. So does that concern you? Maybe it should. We'll talk about that a little bit in a second. So now, again, we have this signature. We need the key associated with it. Please give us the key for root. Root is going to give us back the key and the signature on the key. Well, that's fantastic. We've now gone as high as we can on the chain. So what do we do now? This is kind of problematic, right? Because we've done all this lookups and everybody gave us what we think may be possibly good information, but we're not able to prove anything because we've still used completely open transport to do these lookups. Well, DNSSEC is based on what we call a chain of trust. And you've seen us just now build a chain of trust. At the top of these chains are what are known as trust anchors. Now, trust anchors must be gathered and added to the server configuration on the validating recursive server through a leap of faith. Well, a leap of faith is something that, you say, okay, well, I've done as good a job as I possibly can, and I trust you. Well, if you remember in the movie The Matrix, one of the things that Neo had to do in one of his early investigations into the Matrix was literally take a leap of faith. And he failed miserably. If you remember the first time that he jumped off the building, he ended up squashed. Well, he didn't squash because it was the Matrix. This is the same type of thing that we're looking at. Well, how do you go about lessening the danger of the leap of faith? Do you go out and you just say, hey, well, I saw this you know, I did a DNS lookup and I found this key and I'm just going to put it into my configuration. Well, you might be willing to do that. But you can also go out and look for some other places to find the trust anchor. You can go out to the IANA website and find the DS records or find the key, the public portion of the key that was used to sign the root. You can go out and do queries of the DNSKEY resource record from the root from multiple places and over TCP. So one of the things that I did early on was I had a couple of different virtual machines all throughout the world and a couple of hosted systems. And I would go out to a couple of different ones in different locations in different countries, do queries of the root for the DNS key. And if they all matched, if everything I got back matched, then I knew that what I was looking for was valid. And so I would then be able to use that information and put it into my configuration as a trust anchor. Now, a long, long time ago, COM wasn't signed, org wasn't signed. You know, all of these, the top level domains weren't signed, but there were organizations that were doing DNSSEC, even though they didn't have proof all the way up to the root. So in this case, if there was a break in the chain, for example, COM not being signed, you had to work a little bit harder at gathering these trust anchors. So you would actually literally go out to an organization and find their specific trust anchor. You would insert it into your configuration, and then it worked until it didn't. And the time that it didn't is when they changed their keying material. It was very difficult because I would collect, you know, I would get the example.com DNS key. I would create a trust anchor based on it, and then they would do a key rollover. And that changes their keying information. And when that happens, my trust anchor is no longer valid, and example.com would vanish from my DNSSEC signed information. So we had to work harder, not only to collect the information, but to make sure that it was continually valid. So BIND uses trust anchors from a trusted key statement or a managed key statement. There's actually a newer one that we'll talk about later when we talk about the 9.16 additions to DNSSEC or to BIND. You're going to actually, in your configuration, create a trust anchor with a trusted keys statement. So in this, you're actually going to go out and you're going to put the keying material as found in the root zone for the key, and you're going to stick it into a trusted keys statement. Once you've done that, that's creating a trust anchor at the root. So you see the dot that's in quotes. That's where the chain begins. And from there down, as long as we have DS records, associated DNS keys, and associated signatures, we're able to see that everything is valid all the way down. So trust anchors contain the information capable of validating the keys used to sign the data in this case, the root zone. The trust anchors are made up of the keying material. So again, we would go out and we would look up root DNS key. We would actually literally take the information, the 257.3.8, and then the encoded keying material and put it into our trusted key statement, and then we would have a trust anchor in place. So we've gone through this entire chain. We have all this data in place. How do we actually go about proving that the data is valid? Well, we're going to compare it to a trust anchor. So in this case, we're going to say, oh, look, we have the trust anchor for the root. So it is a copy of the public key for root. Well, if the trust anchor is equal to that DNS key, then we're able to say that, yes, that data was good. We're able to look at the signature of the COM zone or of the DS record and see that the delegation signer record for COM was good, which is going to be able to prove to us that the DNS keys in COM were good, which is going to be able to prove to us that the signatures on the DS records in example.com were good, which are going to be able to prove to us that the signatures on the DNS key was good. And now we're able to prove that we have the good public portion of the DNS key. So we're now able to finally see that, yes, sure enough, we have a validated answer for www.example.com A record. And we still haven't told the client anything about this. So we've gone through and we've done all of this work. We've validated all of this information, but the poor guy is still waiting for an answer. So let's go ahead and send him back the data. We're going to send back the www.example.com A record. He's going to be happy. Yay, he got an answer. Now, it says there that the AD bit is set. That is a possibility, but is not necessarily the case. Well, actually it is. If it's DNSSEC validated, you're going to get back the AD bit. It may actually come back with the signature data if you send the DO bit. You can set the AD bit. It's going to go out to the recursive server and come back with the AD bit set if the data was validated, without necessarily getting back the signature data. So if you're only wanting to see if the AD bit was set, then in your client, set the AD bit. It's going to get echoed back AD set if it was validated and 0 if it was not. So now we have all of this information. Now I talked a little bit, I mentioned the fact that we've now delayed a lookup for www.example.com for an additional tremendous number of lookups plus a whole bunch of complicated mathematics. That's all fine, because now that we've done this, all of this information is cached the same as it would have been with a regular lookup, and it is cached that it has already been validated. So now if someone goes out to example.com and looks for ftp.example.com, they're going to get back ftp.example.com A record, the signature on that ftp.example.com. The server already knows the DNS keys and all of the validity chain upwards, so we're going to be able to do that validation immediately and give the answer back almost as fast as a non-DNSSEC lookup. Yes, of course, it is taking longer for the very first person, but that's what happens when you run on the bleeding edge. Yes, it's going to take longer for your cache to be built, but once the cache is built, then you're in good shape as far as moving forward with speedy DNSSEC validation. And again, we've already done the lookup on COM DNS key. So if instead of example.com, I wanted to go out to google.com, I already have the COM DNS key, so I don't have to go all the way up to the root doing validation all the way up. Again, I'm short-circuiting a lot of that because of the ability for DNS to do caching. So again, you see at the bottom that we might possibly get back the signature on the A record if the client set the DO bit in the outbound query. Now, unfortunately, I've kind of made this a little bit easier than it should have been. The sequence was a little bit oversimplified because there are 2 keys involved in each zone. And I'm going to talk about this again in detail in the coming weeks. There is a zone signing key and a key signing key, unless you're using something new called the CSK, the common signing key. And in this case, you're using one key instead of the ZSK and the KSK. But at this point, we're going to assume that most people still use 2 keys, a ZSK and a KSK. The one for signing the authoritative records in the zone are the ZSK, and the one used for signing the keys, specifically the key records, is the KSK. And again, only the final result was validated. We're going to actually need to do validation on each of the individual steps. And this chain was absolutely vertical. There were no CNAMEs, there were no major oddball referrals, there were no other things that were strange. So this was a very, very simple DNSSEC resolution. And again, it was simplified. But trust me, If you understand what I just went over, then you understand what you need to know to do DNSSEC validation. So with that said, and I do see that, again, I'm running pretty well. It's only 1:35. So are there any questions or comments regarding the resolution process as it was explained today?
I have a question. This is coming out of the chat from Salvador Sosa. He's really wondering about the validity interval. How long can you cache those signatures, and is there a default?
Well, the signatures and the information in those records is going to be stored the same length as the TTL of the associated records. Now, when we start talking about doing key rollover, we're going to start talking about the actual key validity. Well, okay, so let me back up just a second. DNSSEC keys don't have a validity period. Okay, they are, you can use one key forever. I don't necessarily recommend it, but you could do that. The thing that has a timer is the signature data. So you create a signature on a given resource record, and it's valid for a given length of time, and that data is actually encoded in the signature. We'll see that next week. The data that you're going to cache, the length of time that you cache, is the TTL of the resource record. DNS, the server, doesn't really look at the validity interval of the data except when it's doing validation. It doesn't do it for the length of the caching. Now, where that's going to run, where you're going to run into issues with that is when you have some resource records that have very long TTLs, but you want to roll the key quickly. And again, we'll talk about this probably not next, in fact, I know not next week or the week after. When we start talking about doing key rollover, I will go into detail about how you manage the TTL of the record versus the validity interval of the signatures, and we roll all of that up into basically a very simple way of figuring out when you can move on to the next step of the DNSSEC signing process.
So there's a related question. I will also get to the questions in the Q&A, but a related question that came in via chat from Dean. Is there some authoritative source for getting the root DS and updating it?
Well, the root, so there actually isn't a root DS. The DS record is basically just the hash of the public portion of the key signing key from the child. So there is no DS record specifically for the root. What you're going to get is the DNSKEY resource record from the root. Now, yes, you can do it by doing a dig.DNSKEY plus TCP, do it from multiple places, compare the answer. There also is a website. IANA runs, you know, they do the signing of the root. So they have that information on an SSL validated website. So yes, you can find it out of band. Now, one of the other things is that bind nowadays actually comes with the keying material in the code. Obviously, that means that you're trusting ISC to be doing the right thing by providing the correct key, but you're already trusting ISC to run, you're running our code on your server. So, there's a pretty good level of trust there. So the keying information is already embedded. It's already visible. When you do a make install, there's going to be a keys file created in your configuration directory that has the keying material in it. So it's already there. Or you can go out and look at IANA's website, or you can do the digs against the root, or do all of them. That would be the best.
Okay, I've got another question. Does DNSSEC change the randomization of the order of an RR set being returned?
Well, that's an interesting question because, okay, yes, RR sets, as they're returned, they're in the RFC said that there is no defined order in which they will be returned. So the data is returned in the order that is provided from the authoritative server. It's not sorted in any way, so it's still randomized, but to create the hash, and we'll talk about this as we get into the RRSIG resource record information in the next week or so. To create the hash, obviously it has to be ordered, the data has to be ordered. So the RRSIGs are sorted in canonical order before the hash is done. So even though they're returned in the quote unquote random or unsorted order, to create the hash, some work is done to make sure that the hash is actually the same as the one that was created on the authority. So it doesn't, you still are going to get the data back in a randomized order, but to make use of it in the hashing to prove the validity of the signature, you're going to bind, or your recursive name server is going to sort them. But as far as the application, as far as the client, they're still going to get it in a random order. So a little bit more detail than probably was asked for, but that's the way it goes.
Okay, here's another question. Would you advise that companies take responsibility and cache popular sites to avoid delays?
That's up to client base. Honestly, the length of time that we're looking at is a half a second for the very first person that does the query. And when I say a half a second, that's at the very, very high end. A lot of the work that I do is, remote or over a VPN. I'm already seeing delays. That additional, little teeny weeny bit of delay really isn't going to hurt me any. And once it gets into cache, you're not going to have a problem. Newer versions of Bind actually have a mechanism to keep the cache hot. So things that are looked up are automatically, as the TTL is getting close to expiring, it's automatically going to go out and refresh that data. So that's already going to happen, assuming that your very first few clients don't mind that little tiny, delay. So I don't think that proactively doing that is necessarily all that useful.
Okay. Here's another question from David. Are you planning to discuss the use of secondary DNS providers in the context of DNSSEC?
Well, okay, so there's two different mechanisms here. There's the secondary DNS provider, where all they're doing literally is providing a set of secondary servers. And in that case, you doing DNSSEC shouldn't be a problem at all, because in that case, all they're going to be doing is providing the resource records that you give to them, to the clients that ask them instead of you directly. As long as they supply the RRSIGs with the answer when the DO bit is set on a query, then all of that's just going to work. Now, the other type of the secondary system is where, you have outsourced your DNS to a third party. And, at that point, they may have, a button that you click that says do DNSSEC. That's going to be really between you and that provider. So it really shouldn't matter as long as your DNS provider, your secondary service is, using basically today's RFCs and not 8-year-old RFCs. I helped with the deployment of DNSSEC in Portugal for the .pt top-level domain, and this was a number of years ago. I want to say eight or 10 years ago. And one of the things that we discovered the hard way was that one of their secondary servers, so we got the zone signed and we got everything working, we realized after it happened that one of their secondaries was running a very, very, very old version of Bind. And even though they were doing the zone transfers, when they got a query that did not have the DO bit set, they were not returning the DNSSEC, they were not returning the RRSIG. So any information that was received from that server by a client, by a recursive validating client, the data would come back. It didn't have a signature. The client knew it was supposed to have a signature. and therefore it failed validity check. And so the server had to go out and ask one of the other secondaries for the .pt domain. And it was only one of the 7 or 8 that was causing this issue. So it wasn't a big deal. And also at that time, there weren't that many people doing DNSSEC validation. So, not a big deal. But yeah, I think today you're not going to really have a problem with that.
Okay. Another question from Jim. How often do we need to update the root public keys in our caching validating servers so that DNSSEC validation doesn't break? Excellent question.
And the answer is use a new version of bind and it's going to be automatic, sort of, kind of. So there is a mechanism now that we recognize that there's a new key in the root and it automatically takes over. The initial idea was that the root key would roll over every 5 years. It actually took them significantly longer than that, and the key rollover just occurred, it just happened and nobody really noticed there. I mean, well, obviously those of us that do DNSSEC noticed, but because, everybody said, oh my gosh, it's gonna happen. It doesn't happen that often. The root key, the key signing key doesn't change very often, and most likely you're going to be updating software, and the software is going to be able to take into account those changes. But yeah, just if you feel like it, just do a dig.DNSKEY, save it out, save the result out, do it again tomorrow, and diff the two, and see if anything changed. It shouldn't, except when it does.
Well, there's generally quite a lot of kerfuffle on Twitter every time they change it anyway. So
oh yeah.
I'm not recommending Twitter
lots of kerfluffle
as Twitter as a security process. So there's a comment from David to the prior discussion about secondary providers. He says he's tested multiple DNS providers and they do not support DNSSEC as a secondary provider.
Well, then don't use them.
Well, I think there is certainly an issue. There are plenty of hosting providers that don't
If you
DNSSEC.
find one, ask them. Do you when you get a DO bit set, do you provide the DS, the RRSIG associated with the record? And if the response is what, then find a different provider.
Okay, another question from Salvador. I'm paraphrasing a little bit, but he's concerned that DNS load balancing is not compatible with DNSSEC unless you're running the authority server because of the issue of the order of the records in the answer.
No, that shouldn't actually be a problem. Where you do run into problems is some of the global load balancers that don't provide back the entire resource record set. So let me, as an example, there's a load balancer out there that recognizes that the query is coming from Europe. Well, it provides back a different set of A records for Europe than it does from North America or South America or, Asia. Depending on, if you do that, then you do have some issues because the signature is really made up of, it takes the entire resource record set, creates a signature on that entire record set. If you only send back a portion of that record set, then the signature doesn't match. So there are, talk to your load balance providers because there are devices that do this correctly. Some of them may actually generate the signature on the fly. So, the load balancer has your private keys in the load balancer. And when the query comes in, it recognizes that it's from Europe. It creates the resource record set that is for Europe. It creates the signature right then and there and sends the answer back. The problem that I see with those is the fact that your private portions of your keys are now being distributed outside of your protected core. Your load balancers are usually sitting out on the periphery somewhere. You're now putting data that is, really, really important to be kept completely private out on those devices. So again, there's a lot of trust that you put in your load balance provider to do that type of thing. The other thing that can be done is that you put the devices that are going to be load balanced outside of your DNSSEC signed zones. You know, just because you have signed example.com does not mean that you have to sign the subzone GSLB.example.com. You know, if all of your load balancing stuff is, you know, or all of the things, all of the targets of your load balancing are not DNSSEC signed, you know, if you can get away with that, then that's easy and it works with all of the load balancers.
Okay, I see one more question. This is also from Salvador. If someone intercepts the answer to the authority server with the DO bit and creates an answer without DNSSEC, will this fool the server to believe that the zone is not DNSSEC enabled?
No, because, and this is actually a stumbling point for a lot of organizations, and we'll talk about this again a little bit later in the series, but if a zone has a DS record in the parent, then it must be DNSSEC signed. So that means that if you have a zone and somebody has intercepted and has ripped out the RRSIGs or the DNS keys or whatever, the lookup is going to see that there's a DS record in the parent. There's no signatures, you know, no associated DNSSEC records, and it's immediately going to fail. It's going to fail the entire zone, or at least that record. So when I said that caused some problems with some organizations, the way that you back out from doing DNSSEC is not just to rip out all the records in your zone, because what happens, you know, you go in, you sign your zone, everything's working perfectly and you're testing, you send the DS record up to your parent. Now you have the chain of trust in place. Well, you go about doing a signing, you know, or a rekeying event. You rekey and something breaks. And now all of a sudden things aren't validating and you've got bad keys running around, you got bad signatures over here and there and wherever. You say, oh my gosh, you know, the easiest thing to do is just rip out all of this DNSSEC stuff and start over with a clean zone. As soon as you do that, there's a DS record still in the parent. And now anybody that tries to do validation or that is doing validation is going to see that DS record and say, oops, your zone is gone. And that's going to take out the entire zone.
So I've got one last question. It's really a good one to end on because it's kind of a meta question. And this is from Chris Dorsey. Given that DNS security is important to most enterprises, and yet DNSSEC adoption is still extremely low, do you have any ideas why that is?
Because everybody thinks it's really, really complicated, and the mechanisms that we've put in place to make DNSSEC work have been for engineers. You know, the early versions of bind, when you tried to sign a zone, if you put arguments in the wrong order on the command line, you would blow up your zone. A lot of organizations are very risk averse. I was teaching this class a long time ago in Rome and had a representative of a bank that was taking the DNSSEC class. And he said, you know, I've looked at this and I would love to implement this, but our risk assessment team is going to look at this and say, if it gets botched up, then our entire bank is going to go offline. As opposed to somebody coming in and taking over, you know, a little tiny portion of, you know, a couple of customers, and we can easily take the risk of those couple of customers rather than the risk of the entire bank going offline. Well, nowadays, and you know, I've been playing with the 9.16, the new code that's come out, and the DNSSEC stuff that's in there, the new CASP tool is freaking amazing. It makes all of this class almost, you know, other than understanding what it's doing, it makes it so easy to work and work right that everybody ought to do it. The problem is that everybody has always seen DNSSEC as that really, really hard thing. There's been a lot of misinformation about how DNSSEC works. you know, oh, I deployed DNSSEC and everybody's going to be able to look at all of my DNS data, again, because of NSEC. There have been a lot of negatives, and a lot of those negatives have been because of basically misinformation and difficult implementations. Hopefully all of that stuff is going away. I want people to do it. I want people to deploy DNSSEC. You're going to see by the end of this series, it really is easy to do. Make it happen.
Okay, well, that's all the questions we have. So I think we're done for this week.
Okay. Have a wonderful week, everybody. Stay safe. Have a good week, and hopefully I'll see you next time.
Thank you.